When we make solutions in labs, sometimes we make up exactly the concentration we need. And in that case, of course, we are looking at the molarity for our concentration, moles per liters. And we're usually making these in a volumetric flask, which has a long skinny neck and a fill line, and then it holds whatever volume that we're talking about with a high degree of precision. So depending on which volumetric flask we're talking about, we might use a 1 liter volumetric flask, we might use a 500 milliliter, 250 milliliters, whatever it is. So when we're measuring the mass of a material that is going to go in here, we're going to be measuring out grams. And of course, we've measured the grams based on our relationship that our molecular weight is grams per mole. So if we need to know how many moles we want, then like usual, we are dividing grams by the molecular weight to get the number of moles. So we can measure out a certain number of grams. We know how many moles it is. We put it in our flask, and then we dissolve it, and we make that solution. Okay? So when we're doing this, sometimes we just make the solution and then we use it. There are other times where we make this solution because we know not only do we need this main concentration of the solution, which we would call a stock solution, but we're actually going to do a bunch of dilutions. And we're going to take a little bit of this stock solution and we're going to put some in a smaller volumetric flask. Let's say maybe we put 1 milliliter in our first volumetric flask, and then we fill it up to a total of 100 milliliters, which is the whole volume of this smaller volumetric flask. And then let's say we take another volumetric flask and we put 2 milliliters of our stock solution in, and then again we fill it up to the fill line at 100 milliliters. And then maybe we make a third one that has 5 milliliters in it, and again we fill it up to 100 milliliters. And then maybe we take another one and we put 10 milliliters of the stock solution in it, and then fill it up to 100 milliliters. And if we do this, now we have made a series of dilutions that create a serial dilution, is what we call it. It just means a series of dilutions using the same stock solution. So now each one of these has a different concentration. And this original stock solution has its own stock concentration, which I'm just going to call M sub 1, just for convenience sake. Okay? So this isn't just an arbitrary example here where we take a stock solution and then we create a bunch of solutions from it that are more dilute than our original solution. This is actually a scenario that I do in the Chem 331 class, which is called quantitative analysis. And in this class, our original solution would be made by taking 0.2810 grams of an iron-containing compound. And this iron-containing compound is iron, and then we have 2 NH4 plus, and then we have SO4 2, and then there's a dot and it says 6H2O. So this is probably the wackiest chemical formula that you've seen so far. We would take this compound, and I'll talk about this in a minute here, and we would dissolve it to make 1 liter of solution in a volumetric flask. So how many significant digits do we have here? 4. Right, so we're making a solution that has 4 significant digits. So we're going to follow this. And it's important when you're doing analytical chemistry that you have lots of significant digits. So our original solution is this wacky iron compound. So let's take a look at this for a minute. So if we have something that has water molecules stuck on here, this is called a hydrated compound. Just like when you drink water and therefore you are hydrated, some compounds they absorb water from the air, and what we really call it is we call it adsorbing. When something is absorbed, so it's got a B right there, that means that it is going into the material. Like if you think about using a towel to absorb some water that you've dropped on the floor, then the water sinks into the towel and sort of gets incorporated into it. So it goes inside. Whatever is being absorbed goes inside the material that is absorbing it. When we say that something is adsorbed with a D, it sticks to the outside. So when I drive and dust sticks to my car, that dust has adsorbed onto the outside of my car. It doesn't go inside my car's material, it doesn't like somehow get incorporated into the paint or anything like that. It just sticks on the outside. So that's what adsorbing is. And so some compounds have water molecules that stick on to their rest of their compound unit, and they just kind of get stuck. And those are called hydrated compounds. And that's what's happened in this case. We would, in fact, we don't have to worry about the exact naming here, but this is a special kind of material. This is called an inorganic complex. And we would actually call this, because there's 6, that's hexa, right? So this would be a hexahydrate. All right, I am not going to test you on this, but I thought you might be interested in it. So let's take a look at this crazy compound here. We've got iron, and we've got this NH4, but wait, isn't this an ion? This is a cation, right? NH4 plus is the cation that's here. And then we've got sulfate ion. So let's take a look at the parts of this FeNH4 2 SO4 2 hexahydrate. So this is an iron ion, but what is the charge on it? Let's check it out. So we know that this is neutral overall. So what about all the pieces? What's the charge on a water molecule? We just write H2O, right? So this also is neutral. There is no charge on a water molecule. What about this guy? This is sulfate ion, and it is SO4 2-. So each one of these guys has a 2- charge, and there are 2 of them. So 2 times -2 has so far a charge of -4. How about this guy? This is the ammonium ion, NH4 plus. And there are 2 of them. So we have +1 times 2 is equal to +2 so far. And so let's review. We have water, which is neutral. We have -4 from our 2 sulfates, and we have +2 from our 2 ammonium ions. So what's the charge on this iron? Looks like it has to be Fe2+. Okay, so we have an Fe2+, that's fine. And we took 0.2810 grams of this whole crazy compound. And what's our question? What is the molarity of our stock solution? Well, we know moles per liter is our molarity. So let's calculate how many moles we have. So we have 0.2810 grams of this iron compound, which I'm not going to write out because it's really long. So you need to look up the molecular weight and write grams per mole of this compound. So pause the video and go calculate that molecular weight. All right, so check my work, but I got 392.133 grams per mole for this compound. And that's because we have a lot of atoms here, right? We have 1 iron, we have 2 nitrogens, we have 8 hydrogens, 4 times 2, plus another 2 times 6, 12 more hydrogens. So 8 plus 12 is 20 hydrogens. We have 2 sulfur atoms. We have 2 times 4 was 8 plus 6 more, so 14 oxygen atoms. So that adds up a lot. So I got that this gives me 7.166 times 10 to the minus 4 moles of the iron compound. So what's the molarity? It's moles per liter, right? And I have 1 liters. So I'm going to put molarity 1. That was my label on that stock solution. It's just going to be the same. 7.166 times 10 to the minus 4 mole per liter. So this is the stock solution that we're going to use to make a series of more dilute samples that we talked about. I said we were going to take 1 milliliter, 2 milliliters, 5 milliliters, 10 milliliters. This is actually what my students do in lab. So if I take 1 milliliter of this stock solution and I want to figure out what the molarity of that other material is, how are we going to do this? Well, it's super straightforward, right? We have 1 milliliter of our molarity, 7.166 times 10 to the minus 4 moles per 1 liter. So I need to convert my milliliters here into liters. 1,000 milliliters is equal to 1 liter. And this is going to get me what kind of units? Let's take a look. Milliliters cancel, liters cancel. We're going to get moles. So this is going to be the moles of the iron compound. And then we are going to dissolve it in 100 milliliters. So this is something we totally can do, right? We're going to have moles. And if we look at this, this is just dividing by 1,000. So 7.166 times 10 to the minus, what's that going to be? 7 moles of the iron compound go into that first solution. So that's no problem. And then we dissolve it in 100 milliliters. So the molarity of A is 7.166 times 10 to the minus 7 moles per 100 milliliters, which is 0.1000 liters. So the molarity of my first compound is my first dilution is 7.166 times 10 to the minus 6 molar. Okay, so that's our first one. So go ahead and take a minute here and figure out what the other 3 concentrations are, where we take 2 milliliters of our stock solution, 5 milliliters of our stock solution, and 10 milliliters of our stock solution. And go ahead and calculate these 3 concentrations. Pause the video and do that. Okay, so what I got for these was 1.433 times 10 to the minus 5 molar, 3.583 times 10 to the minus 5 molar, and 7.166 times 10 to the minus 5 molar. So what we just have here is a series of more dilute samples that are coming from our stock solution. Right, here's our stock solution. And so let's review the calculation that we did. When we did this original first one, right, M sub A, we took the volume and we took the molarity, and this got us moles, right? And we know that that's true since molarity is equal to moles per liter, moles over volume. If we multiply the molarity and the volume, that's going to get us the moles. Now, what did we do over here? We got our moles on the top, and then we divided by our new volume, just right here, to get our new molarity. But notice that this moles was the same as this moles. So let's look at what that means for us. If I took my volume, and this was my 1 milliliter, right? And I multiplied it times my molarity of the original solution, this gets me moles. This is also the same number of moles that we just dissolved in 100 milliliters to make M sub A, right? This number of moles, 7.166 times 10 to the minus 7 moles, that we got from multiplying 1 milliliter times our molarity, I'm just repeating myself here, is the same thing as this M sub A molarity multiplied by that 100 milliliters. Oops, not 1,000. So anytime you want to do a dilution, what you're really doing is we're just calculating the moles. And then we're taking the moles of that solution and we're dissolving it into a new volume. So it is 100% fine anytime you are doing a dilution problem to just do exactly what we just did. Calculate how many moles by multiplying volume times molarity, and then take that moles, divide it by the new volume, and you're going to get your new molarity. But if you wish to, you can skip this middle step, and you can notice what we have here. I have a volume of my stock solution, and I have a volume of my new solution. So I can rewrite what we just did here as a short version. M1, I guess I have the V's on the left, so I'll go V1 M1 is equal to M2 V2. But be careful here, all right? If M1 is the stock solution and its concentration, then V1 is the volume of the stock solution. M2 is the molarity or the concentration of the more dilute solution. And V2 is the volume of the dilute solution. So you have to make sure that your volume and your molarity get paired up correctly. Let's take a look at some questions that we might use this sort of calculation for. So you might be asked something like, how many milliliters of a 1.694 molar solution of NaOH are needed to make 250 milliliters of 0.5 molar NaOH. So you could just identify volumes and molarities, but I find it better to draw myself a picture, okay? So here's my picture. I have this container of 1.694 molar NaOH. I want to take some of it and I want to put it into a 250 milliliter volumetric flask that has a concentration of 0.5 molar NaOH. The reason why I drew this is because now it's really easy for me to see where my M1 and my M1V1 and my M2V2 are, right? Because my M1 and my V1 are going to be the same solution. So here's my M1, and this unknown is my V1. And that's going to be equal to my M2 multiplied by my V2. So now I can see that I have this number, I have this number, and I have this number, and I just need to solve for this number. So drawing yourself a picture can really help to make sure that you put the numbers in the right places, and I very much encourage you to do this. The other thing that you can notice from this, if I set this up, is that if we were solving for the moles first, then I would need to cancel out, or I would need to convert my milliliters into liters in order to, get them to multiply by that volume or by that molarity there. But here, notice what happens if I have milliliters as my desired unit here, and I set up this equation with these numbers in it. If I divide out the 1.694 molar out of both sides so I can solve for the volume, V1, look what happens to the units. My molarities cancel out, my numbers cancel out, of course, that's what's supposed to happen. My molarities cancel out here, and I'm left with milliliters, which is in fact the volume unit I wanted. So I don't have to cancel units in this case because my molarity units already cancel out and I actually wanted milliliters. Okay, so if I solve this, I will get 73.79 milliliters of my stock solution that I can use then to make my 250 milliliters of 0.5 molar sodium hydroxide. All right, let's try another practice problem. If 15 milliliters of a 2.941 molar HCl solution are diluted to 100 milliliters, what is the concentration? What is the molarity of the new solution? All right, so now that you've seen this once, go ahead and pause the video and try to solve for the new molarity by yourself. All right, so I hope that you drew a picture. I'm going to go ahead and draw a picture. So my picture has my stock solution, which is 2.941 molar HCl. And now I take 15 milliliters of this. And I'm going to put it into my volumetric flask. And this is a 100 milliliter volumetric flask. So I'm going to take this 15 milliliters and it's going to go in. And then I'm going to fill it up with distilled water. And then I need my new concentration. So if I set up my numbers, M1V1 equals M2V2, I can see that this is my molarity M1, this is my volume V1. My M2 is my unknown, and my V2 is this 100 milliliters. So if you solve for M2, you should have gotten 0.4412 molar. Now, the two example problems that I gave are basically the two forms that you will see that are at least the standard forms of calculating for a new molarity. And notice that we will always have 3 out of 4 of these unknowns, okay? Now, it's always possible that somebody will have you calculating grams first or something like that, so that, maybe the molarity of the initial solution is not given, or maybe it tells you how many grams you end up with in your final concentration. But bottom line, you have to have 3 out of 4 of these quantities in order to do this kind of a calculation. So hopefully you have seen that doing dilution calculations is just one small extension from all of the calculations that we are already doing, and it's just focusing again on the definition of molarity as being moles per volume in liters, and that you don't actually have to memorize this equation. You can just use the definition of the molarity and solve for moles, and it will work exactly correctly every single time.